Picture this: you're gliding through the cosmos, not at the sluggish pace of a rocket, not even at the breakneck speed of a shooting star, but at the ultimate velocity of the universe itself, the speed of light. In 1 second, you'd circle the Earth 7.5 times. In just over 8 minutes, you'd reach the Sun, and in a little more than 4 years, you'd arrive at our closest stellar neighbor, Proxima Centauri. But here's the cosmic twist: even at this unimaginable speed, you'd still be crawling through the vastness of space, because when it comes to the universe, light doesn't always play by the rules we think we know. What if I told you that light speed isn't always the constant, unwavering number we learn in school? That under certain extreme conditions, light can slow down, speed up, or even appear to bend the very fabric of reality. From the crushing depths of black holes to the bizarre quantum realms where particles flicker in and out of existence, the speed of light becomes a wild, unpredictable force. And that's just the beginning. Across the cosmos, there are places where light races at velocities that defy logic, where time itself stretches and warps like taffy, and where the universe reveals its strangest, most dazzling secrets. That's exactly what we're diving into today: 30 mind-blowing facts about the universe's most extreme speeds of light. We'll explore how light can be frozen in its tracks, how it might break its own speed limit, and how ancient starlight holds clues to the birth of everything. You'll discover why some scientists believe light could be the key to unlocking hidden dimensions, and how, in the void of space, a single photon's journey can take billions of years. This isn't just a tour of cosmic trivia, it's a front-row seat to the universe's greatest light show. So buckle up. By the time we're done, you'll never look at a ray of sunshine or the night sky the same way again. Hold onto your textbooks, because that number you memorized, 299,792 kilometers per second, isn't always the full story. Light's top speed is like a cosmic speed limit in the vacuum of space, but the moment it hits anything else, water, glass, even Earth's atmosphere, it suddenly hits the brakes. Think of it like a superstar athlete sprinting on a track, only to plunge into a pool mid-race. In water, light slows to a crawl of around 225,000 kilometers per second. Through glass, even slower. This isn't some glitch in the universe. It's all thanks to a property called the refractive index, which measures how much a material bends and slows light. Here's the wild part: this slowdown isn't just a lab curiosity. It's the reason your internet exists. Fiber optic cables, those hair-thin strands of glass that zip data across oceans, rely on light's controlled slowdown to carry movies, messages, and cat videos at nearly light speed. Without that carefully calibrated drag, signals would scatter into chaos. But the real magic happens when scientists push this further. In labs, they've crafted materials so dense with exotic structures that light barely moves, like a car stuck in cosmic traffic. Some experiments have even brought light to a near standstill, freezing its waves in place like a paused movie. And if that sounds impossible, wait until you hear how light can also race faster than its supposed limit. But that's a twist for another fact. For now, remember, light speed isn't a fixed number, it's a dance, choreographed by whatever medium it's passing through. Now here's something that sounds impossible: entire galaxies racing away from us faster than light itself. No, it's not a sci-fi plot twist. It's the universe showing off one of its most mind-bending tricks. Think of space as an inflating balloon covered in dots. As the balloon expands, every dot moves away from every other dot. But here's the catch: the fabric of the balloon is stretching, not the dots themselves. That's cosmic inflation in action. Distant galaxies aren't zooming through space at light-breaking speeds. Space itself is stretching between us, carrying them along like leaves on a rushing river. This cosmic loophole means relativity stays intact. Einstein's famous speed limit only applies to objects moving through space, not to space itself stretching. And the farther apart two galaxies are, the more space there is to expand between them. At some point, that expansion adds up faster than light could ever hope to keep pace. Right now, every galaxy beyond about 14 billion light-years is vanishing from our future view, not because they're moving away, but because the space between us and them is growing faster than their light can bridge the gap. One day, their light will never reach us again. Here's where it gets stranger. We're not special. From any galaxy's perspective, the same thing happens. The universe has no center, just an endless stretch party where every guest sees everyone else speeding away. And this isn't some distant future scenario. It's happening right now, with galaxies we can still see today eventually disappearing like ships slipping over the horizon. So while light speed remains the universe's ultimate speed limit for travel, space itself plays by entirely different rules, stretching the cosmos into an ever darker, ever lonelier expanse. Some of the most thrilling moments in science happen when the universe seems to break its own rules, like in 2011, when a team of researchers made an announcement that sent shockwaves through physics. They claimed to have caught neutrinos, those ghostly subatomic particles, red-handed, speeding past light itself. The experiment, called Opera, had fired neutrinos from CERN in Switzerland through 730 kilometers of solid rock to a detector in Italy. The math said the journey should take roughly 2.4 milliseconds at light speed, but the neutrinos arrived 60 nanoseconds sooner, as if they'd cheated the cosmic speed limit. For a brief, glorious moment, it looked like Einstein might be wrong. Headlines screamed about relativity crumbling, time travel becoming possible, and textbooks needing rewrites. But here's the twist. The universe loves a good plot twist. After months of feverish scrutiny, scientists found the culprit, not a flaw in Einstein's theory, but a loose fiber optic cable and a misaligned atomic clock. The faster-than-light result, a measurement error. The neutrinos had been obeying the rules all along, yet buried in this near miss was something even more fascinating. Neutrinos do pull off cosmic magic tricks, just not breaking light speed. These particles are so insubstantial that trillions pass through your body every second without a single collision. They slice through planets like they're not even there, barely interacting with matter at all. And while they can't outpace light in a vacuum, in dense materials like water or ice, something wild happens. Light slows down, but neutrinos don't. So in places like Antarctica's ice cube detector, neutrinos actually do beat light, not because they're speeding up, but because light is slowing down. It's a reminder that the universe's rules are full of nuance, and even our mistakes can lead to deeper truths. The Opera incident wasn't science failing, it was science working exactly as it should. Researchers chased an impossible result until they found the mundane truth, proving that even when we think we've caught the universe in a lie, it's usually just waiting to teach us something new. It's one of the most baffling phenomena in physics: two particles, separated by galaxies, somehow mirroring each other's actions instantly, as if they share a hidden hotline. Einstein famously dismissed this as spooky action at a distance, refusing to believe anything could communicate faster than light. Yet quantum entanglement, as it's called, defies intuition in ways even he couldn't fully reconcile. Picture tossing two coins into the cosmos, one landing on Earth, the other on a planet light years away. No matter how far apart they are, if they're entangled, one always lands heads up the moment the other does, without any signal traveling between them. How does this not violate light speed's cosmic speed limit? The answer lies in what entanglement doesn't do. Unlike a radio signal or a laser beam, entangled particles don't actually send information to each other. Instead, their states are intertwined from the moment they're linked, like a pair of dice that always roll matching numbers no matter where you throw them. When we measure one, the other's state snaps into place, but there's no energy or message exchange, just a mysterious, unbreakable correlation baked into the fabric of reality. Scientists have tested this over and over, separating entangled photons by hundreds of kilometers and still observing their instant coordination. In 2017, Chinese researchers even used a satellite named Mishus to entangle particles over 1,200 kilometers apart, smashing previous records. The results, same eerie synchronicity, but here's the catch. While the effect appears instantaneous, we can't use it to send messages faster than light. The randomness of quantum states means the person measuring the second particle can't tell if their result came from entanglement or chance until they compare notes the old-fashioned, slow way. Einstein's skepticism wasn't entirely wrong. He sensed quantum mechanics was incomplete, and in a way, he was right. Entanglement doesn't break relativity because it's not a signal, it's a feature of the universe's underlying quantum code, written in a language we're still deciphering. Some theories suggest entangled particles might be connected through higher dimensions or wormholes, shortcuts through spacetime we can't yet perceive. Others propose the particles aren't truly separate at all, but part of a deeper, indivisible whole. What's clear is this: entanglement reveals a universe far stranger than Einstein imagined, where the rules of locality and distance blur. It's not that light speed has been surpassed, it's that the universe has a hidden layer where speed, as we understand it, doesn't even apply, and that's perhaps the spookiest truth of all. What if the universe had an entire class of particles that treated light speed like a minimum speed limit rather than a maximum? Enter tachyons, the hypothetical particles that, by definition, would always travel faster than light. Unlike neutrinos, which flirted with breaking the rules before being caught obeying them, tachyons are theorized to live permanently on the other side of the cosmic speed limit, never slowing down to the pedestrian pace of light. Their name comes from the Greek word tachys, meaning swift, and if they exist, they'd rewrite our understanding of physics in ways that make quantum entanglement look tame. Here's the catch: tachyons aren't just fast, they're required to be. According to some interpretations of Einstein's equations, these particles would possess imaginary mass, a mathematical quirk that makes their existence possible only if they never dip below light speed. It's like a cosmic "you can't sit with us" scenario. The moment a tachyon tried to slow down to light speed, its energy would become infinite, a physical impossibility. Instead, they'd zoom eternally faster, their speed increasing as they lost energy, the exact opposite of how normal matter behaves. Yet for all their theoretical intrigue, tachyons remain ghosts in the equations. No experiment has ever detected one, and their existence would raise thorny questions about causality, like whether they could send information backward in time, creating paradoxes where effects precede causes. Imagine a tachyon-powered message arriving before it was sent, or a signal from the future altering the past. Science fiction loves this idea, from Star Trek's tachyon-based scanners to plots where these particles are used to breach spacetime. But here's the twist: the absence of tachyons might be just as revealing as their discovery. If they don't exist, it reinforces light speed as a fundamental cosmic firewall, a boundary that keeps cause and effect in order. And if they do, well, the universe just got a lot stranger. Until then, tachyons remain one of physics' most tantalizing what-ifs, a reminder that some speed limits might only exist to be broken. Black holes don't just bend light, they torture it. At the event horizon, that invisible point of no return, gravity becomes so monstrous that even light's frantic escape attempts turn into a cosmic standstill. Imagine a sprinter racing up an ever-steepening treadmill. As the incline approaches vertical, their furious strides barely keep them in place. That's light at the edge of a black hole, forever straining against gravity's grip, photons stretched into frozen waves, their energy drained to near nothingness by the sheer weight of spacetime itself. This eerie phenomenon isn't just theory. When scientists modeled the supermassive black hole Gargantua for the movie Interstellar, they consulted physicist Kip Thorne to ensure its portrayal was scientifically accurate. The result, a haunting visual where time distorts like taffy, and light from stars near the horizon smears into a warped halo, frozen in mid-escape. That glowing ring isn't artistic license, it's the real deal. Photons trapped in orbit just outside the event horizon create what's called a photon sphere, a ghostly carousel of light circling the abyss. Stray a hair closer, and those photons plunge inward, swallowed by darkness. But here's the unsettling reality. If you could hover at the event horizon, impossible, but let's pretend, you'd witness the universe's greatest magic trick. Light from distant stars wouldn't just redshift into invisibility, it would appear to stop. Time itself would grind to a halt from your perspective, the cosmos aging billions of years in what feels like an instant. Meanwhile, an outside observer would see your last desperate light signal stretched into eternity, your image fading like a ghost on a cosmic replay. This paradox reveals relativity's cruelest joke. Light speed never changes, but space-time can twist until its progress becomes meaningless. Black holes don't break the rules, they expose them in their rawest form, turning the universe's speed limit into a funhouse mirror. And somewhere in that distortion lies the answer to questions we haven't even learned to ask. Deep in the heart of a nuclear reactor, something impossible happens. Particles actually outrun light itself. Not in the empty void of space where light reigns supreme, but in the crowded atomic lanes of water or glass where light speed drops by 25%. When a high-energy electron, fired from radioactive decay or a particle accelerator, enters this denser environment, it can suddenly find itself moving faster than the local speed limit for light. The result, a breathtaking blue glow, as if the universe itself is sounding an alarm. This eerie phenomenon is called Cherenkov radiation, and it's light's version of a sonic boom, a celestial speed bump where physics turns into pure spectacle. Think of it like this. Imagine a jet breaking the sound barrier, compressing air molecules into a thunderous shockwave. Now replace the jet with an electron, the air with water molecules, and the sound barrier with light slowed down pace. As the electron races ahead, it distorts the electromagnetic field around it, forcing nearby atoms to release energy in the form of light waves. These waves pile up like a cosmic traffic jam, merging into that distinctive cobalt shimmer. The color isn't random. Blue light dominates because higher energy photons are produced more efficiently in this chaotic scrum. The real magic happens in places like nuclear reactors or spent fuel pools, where Cherenkov glow bathes everything in an otherworldly hue. Submarine crews have nicknamed it Reactor Blue, a constant reminder of the power humming beneath their feet. Even nature gets in on the act. When high-energy cosmic rays slam into Earth's atmosphere, they create fleeting bursts of Cherenkov light, detectable only with ultra-sensitive telescopes. But here's the twist. This isn't just a light show. Cherenkov radiation helps scientists track particles too small to see. In neutrino detectors like superluminal, and that blue pulse is often the only sign that a ghostly neutrino has collided with an atom, freeing an electron to race through the water. Without this radiant fingerprint, we'd be blind to some of the universe's most elusive particles. So the next time you see that surreal blue glow in a reactor photo, remember, you're not just looking at light. You're witnessing physics stretch its own rules, a fleeting moment where speed, energy, and light collide in a dance that's as beautiful as it is impossible anywhere else in the cosmos. What if you could cross the galaxy without actually moving faster than light? That's the tantalizing promise of the Alcubierre warp drive, a concept so audacious it bends the rules of relativity without technically breaking them. Named after physicist Miguel Alcubierre, who first sketched the idea in 1994, this theoretical engine doesn't propel a ship through space, it manipulates spacetime itself, creating a bubble where the fabric of the universe does the heavy lifting. Picture standing on a moving walkway at the airport. Your legs aren't sprinting, but the ground beneath you is. In Alcubierre's vision, space-time contracts in front of the bubble and expands behind it, sliding the ship forward while the passengers experience zero acceleration. No g-forces, no time dilation, just a smooth ride to the stars. The math is rooted in Einstein's equations, which allow for space-time to warp in ways that sidestep light speed's hard limit. To make it work, you'd need two impossible-sounding ingredients: negative energy, a hypothetical form of matter that repels rather than attracts, and exotic matter with negative mass to stabilize the bubble. Think of it like building a tunnel through a mountain, except the mountain is the universe, and the tunnel's walls are made of pure speculation. For years, this relegated warp drives to the realm of sci-fi. Then in 2012, NASA EagleWorks lab quietly began probing the edges of possibility. Their experiments focused on the warp field interferometer, a device designed to detect microscopic distortions in spacetime. The results inconclusive but provocative enough to keep the dream alive. Here's where it gets wild. Even if the physics checks out, the energy requirements are monstrous. Early estimates suggested powering an Alcubierre drive would need the mass energy of Jupiter. Later refinements whittled it down to maybe the mass of a small moon, still absurd by today's standards. But breakthroughs in quantum physics hint at ways to shrink that demand further. Some theories suggest harnessing dark energy, the same mysterious force accelerating the universe's expansion, could one day provide the necessary kick. Others propose that advanced civilizations might use black holes or cosmic strings as shortcuts, weaving spacetime like a loom. The biggest hurdle isn't just energy, it's causality. A warp bubble could, in theory, create closed time-like curves, allowing travel to the past and opening a Pandora's box of paradoxes. Imagine arriving at your destination before you left, or worse, triggering a chain reaction that unravels history. This isn't just academic worry, it's why many physicists treat warp drives as mathematical curiosities rather than blueprints. Yet the fact that the equations allow such possibilities at all is a humbling reminder of how much we still don't understand about the universe. For now, Alcubierre's warp drive remains a beautiful thought experiment, a testament to human ingenuity's refusal to accept impossible. It's not a working engine, it's a challenge, a beacon for future physicists to either debunk or chase down. And maybe that's enough. After all, every revolutionary technology begins as someone's wild daydream. The Wright brothers were once told flight defied the laws of physics. The atomic bomb was pure fiction until it wasn't. So while we won't be warping to Alpha Centauri next Tuesday, the mere fact that scientists are crunching the numbers means the dream hasn't been grounded yet. And in a universe this strange, that's worth holding on to. Gamma-ray bursts are the universe's ultimate fireworks, cosmic detonations so violent they outshine entire galaxies for a few fleeting seconds. Packed into those moments is energy equivalent to what the Sun will emit over its entire 10 billion-year lifetime, all focused into twin jets screaming through space at nearly the speed of light. These aren't just fast, they're precision-engineered death rays, narrower than a laser pointer but stretching billions of light-years across the cosmos. And the engine behind them, one of nature's most catastrophic events, the collapse of a massive star into a black hole. Here's how it unfolds. When a star 20 times heavier than the Sun exhausts its fuel, its core implodes in a fraction of a second. The outer layers crash inward, then rebound in a supernova explosion visible across the universe. But deep inside that chaos, something even wilder happens. The collapsing core forms a newborn black hole, and as it devours the surrounding star matter, magnetic fields twist into cosmic particle accelerators. These fields funnel debris into twin jets along the black hole's spin axis, where matter gets whipped to within a hair's breadth of light speed. The jets punch straight through the dying star like bullets through tissue paper, and when they break free, they unleash the gamma-ray burst, a pulse of high-energy light so intense it can be detected halfway across the observable universe. What's staggering isn't just the speed, but the efficiency. These jets convert raw stellar death into focused energy with almost no waste. Imagine setting off a nuclear bomb and directing 99.99% of its blast into two pencil-thin beams. That's the cosmic precision at work here, and because the jets move so close to light speed, relativity warps their behavior. Time for particles in the jet slows to a crawl from our perspective, while the light they emit gets squeezed into higher energies, creating the gamma rays we detect. The aftermath is just as surreal. As the jets plow into surrounding gas, they create shockwaves that glow for weeks or months, an afterglow visible in X-rays, radio waves, and even visible light. In 1997, astronomers caught one such burst, GRB 970508, and traced its fading light to a galaxy billions of light-years away. That single observation proved gamma-ray bursts weren't local oddities but universe-spanning beacons, marking the births of black holes across cosmic time. But here's the real kicker. If one of these jets happened to point at Earth from within our galaxy, the results would be catastrophic. The high-energy radiation could strip away our ozone layer, triggering mass extinctions. Some scientists even suspect a gamma-ray burst might have contributed to the Ordovician extinction 450 million years ago, when 60% of marine life vanished. Thankfully, the nearest potential candidates, like the star Eta Carinae, are safely distant. Still, these bursts serve as a humbling reminder: light speed isn't just a curiosity. In the wrong hands, or rather, the wrong cosmic events, it's a weapon of planetary-scale destruction. Yet for all their fury, gamma-ray bursts are also cosmic gold mines. They're like interstellar lighthouses, their light piercing through dust and gas to reveal the early universe's structure. Some of the most distant bursts ever detected let us peek back to when the first stars were forming, their jets acting as backlights to illuminate primordial hydrogen clouds. Others have helped test Einstein's relativity with precision unmatched by any earthly experiment. Even their afterglows serve as labs for studying how matter behaves at near light speeds, giving us front-row seats to physics we could never replicate on Earth. So the next time you see a fleeting blip on a gamma-ray telescope's readout, remember, you're witnessing the universe's most extreme particle accelerator in action, a natural supercollider where black holes birth beams of matter moving so fast they blur the line between energy and light. And somewhere in those beams lies a clue to how the cosmos turns chaos into something eerily, beautifully precise. Imagine you and your twin decide to part ways. One of you boards a spaceship hurtling toward a distant star at 99% the speed of light, while the other stays behind on Earth. When the traveling twin returns after what feels like a few years, they step out of the ship to find their Earth-bound sibling has aged decades. This isn't science fiction. It's the twin paradox, one of Einstein's most jaw-dropping predictions. Time doesn't just feel slower when you're moving fast. It actually is slower thanks to a phenomenon called time dilation. At everyday speeds, this effect is too tiny to notice. But as you approach light speed, time warps in ways that defy intuition. For the astronaut racing through space, clocks tick normally, meals digest as usual, and a 5-year mission feels like 5 years. But from Earth's perspective, their time stretches like taffy. The faster they go, the more pronounced the effect. At 99.9% light speed, 1 year for the traveler equals 71 years back home. Push it to 99.99%, and that ratio skyrockets to 1 year versus 7,000. Here's the kicker: we're not just talking theory. Your phone's GPS relies on correcting for time dilation every second. Satellites orbit Earth at about 14,000 kilometers per hour, fast enough that their onboard clocks tick 38 microseconds slower each day than clocks on the ground. But they are also higher in Earth's gravity well, which speeds up time by another 45 microseconds daily. Net result: if engineers didn't account for relativity, GPS locations would drift by about 10 kilometers per day, leaving you lost in your own neighborhood. The strangest part, both perspectives are correct. From the satellite's viewpoint, Earth's clocks are the ones running slow. There's no universal now. Time is as flexible as space-time itself. This isn't just a quirk of engineering. It's proof that the universe plays by rules far stranger than our daily experience suggests. And somewhere in that cosmic flexibility lies the key to unlocking journeys across the stars without losing everyone you love to the relentless tick of time. What if the speed of light wasn't always the speed of light? Wild as it sounds, some theories suggest that in the fiery chaos of the early universe, light might have raced across the cosmos faster than its current limit. This isn't just a tweak to physics, it could solve one of cosmology's biggest head-scratchers: why the universe looks so eerily uniform in every direction. Picture the universe just after the Big Bang, a seething plasma so dense that light couldn't travel more than a hair's breadth before being absorbed and re-emitted. Today, that primal fog has cleared, leaving the cosmos transparent. But here's the puzzle. Regions of space now billions of light years apart somehow reach the same temperature long before light or anything else could have shuttled between them. It's like walking into a concert hall where every instrument is perfectly tuned, even though the musicians never met to rehearse. Enter variable speed of light theories, where the rules of physics weren't as rigid in the beginning. Proposed by physicists like Joel Megiddo and Andy Albrecht, these ideas suggest that light may have briefly outpaced its current top speed during the universe's first sliver of existence. This temporary cosmic cheat code would explain how distant regions synchronized so flawlessly information could race across the newborn universe before space-time locked light into today's speed limit. The mechanism hinges on inflation, the theory that the universe underwent a hyper-fast expansion in its first trillionth of a second. But instead of inflation stretching space itself, a faster speed of light could have achieved the same result, connecting far-flung regions before they were ripped apart by expansion. Some models even suggest this shift was triggered by phase changes in the early universe, like water freezing into ice, where the fundamental constants of nature crystallized into their current values. Critics argue this is a solution in search of a problem, since inflation already explains uniformity neatly. Yet the idea persists because it offers something inflation can't: testable differences in the cosmic microwave background, the afterglow of the Big Bang. If light's speed once varied, it would leave faint fingerprints in this ancient light, subtle patterns that telescopes like the Planck satellite might one day detect. The most radical versions of the theory go further, suggesting that light's speed isn't just a historical fluke, but could still fluctuate in extreme environments like near black holes or in quantum foam. It's a reminder that the constants of nature might be more like habits patterns the universe settled into after an unruly youth. And if that's true, the speed of light isn't just a number. It's a cosmic accident frozen in time. Photons are the ultimate cosmic speed demons, massless particles that hit the universe's speed limit without even trying. But if they weigh nothing, why can't they go faster? The answer lies in Einstein's most famous equation, E equals mc squared, which reveals a startling truth: speed isn't just about mass. It's about the very fabric of reality. Think of it like this: as an object accelerates, its energy doesn't just increase linearly, it balloons exponentially. To push a spaceship from 90% of light speed to 99% requires far more energy than going from 10 to 20%. Why? Because relativity treats space and time as a single, stretchy entity. The closer you get to light speed, the more your motion through space gets converted into a distortion of time. At light speed itself, all your energy becomes pure momentum. There's nothing left to convert into extra speed. Photons having zero mass are already maxed out. They're not slowed down by the baggage of mass, but they also can't tap into reserves they don't have. Here's the cosmic irony. Being massless isn't a free pass to infinite velocity. It's more like being stuck in the fast lane with no exit. Photons don't experience time or distance from their perspective. The moment they're emitted is the same instant they're absorbed, whether they're crossing a light bulb or a galaxy. But that's the catch. Relativity doesn't just limit how fast you can go through space. It defines how space and time trade places at extreme speeds. For light, the journey is instantaneous, but for us, it's a measurable crawl across the cosmos. This isn't just theoretical nitpicking. Particle accelerators prove it daily. Electrons, which have a tiny mass, can be boosted to 99.9999% of light speed, but that final fraction is where the universe slams the brakes. The energy required to close the gap approaches infinity, like trying to fill a bottomless cup. That's why CERN colossal machines can hurl protons with the energy of a freight train, yet never quite match a photon's pace. Some theories, like loop quantum gravity, flirt with the idea of light speed varying in extreme conditions like near the Big Bang or inside black holes. But even then, the change isn't because photons suddenly get faster. It's because space-time itself might be pixelated, altering how distances and times interact. So while light speed might not be universally constant, its supremacy remains unshaken. Photons aren't lazy, they're just playing by rules written into the bedrock of existence. And that's the real twist. The speed of light isn't about light at all. It's the universe's ultimate exchange rate, the conversion factor between space and time, energy and mass. Photons don't choose to go this fast. They simply embody the universe's deepest balance, a speed limit woven into the cosmos long before stars flickered to life. Mess with it, and you're not just tweaking physics, you're rewriting reality itself. Light may hold the cosmic speed record, but darkness has a sneaky trick up its sleeve. It can appear to break light's limit without breaking a single law of physics. Take something as simple as swinging a laser pointer across the moon. If you flick your wrist fast enough, the dot can race across the lunar surface faster than light itself. But here's the catch. No actual object or information is moving faster than light. You're not seeing a photon sprinting across the moon. You're witnessing a chain reaction of darkness and light, like flipping dominoes where each tile falls at light speed, but the wave of collapse seems to outpace them all. This illusion works because darkness isn't a thing, it's the absence of light. When you sweep a laser beam, the dot isn't a physical object traveling from point A to B. Instead, new photons from your laser continuously hit different spots on the surface while the previous ones vanish. If you aim at the moon and ignore atmospheric scattering, each photon still takes 1.3 seconds to get there. But if you swing the laser fast enough, the dot's apparent motion between 2 points can exceed light speed because no single particle is making the trip. It's like flashing a spotlight across a distant mountain. The beam's movement isn't bound by light's speed limit because it's just a pattern, not a real object. Scientists call these superluminal shadows, and they pop up in the cosmos in bizarre ways. When a pulsar's lighthouse-like beam sweeps past dust clouds, the shimmering glow can appear to race faster than light. Even eclipses pull this stunt. If Jupiter's shadow could graze Earth's surface at a shallow angle, the shadow's edge might technically outpace light for a fleeting moment. The key word is technically. No energy, matter, or signal is breaking relativity's rules. It's just geometry playing tricks on us like a cosmic sleight of hand. The real magic happens when you realize this isn't just a parlor trick. It's a masterclass in how relativity really works. The universe doesn't care about illusions, it guards information fiercely. You could sweep a laser dot across a galaxy at 1 trillion times light speed, but you still couldn't use it to send a message faster than light. The first photon carrying the start of your signal would always arrive before any later photons, preserving causality. Shadows, after all, can't carry data, they're just the universe's way of drawing with disappearing ink. this quirk reveals something profound. Light's speed limit isn't about motion, it's about connection. The cosmos draws a line between what's possible and what's merely apparent, ensuring no event can influence another faster than light can bridge the gap. So while darkness might win a pixel race now and then, light still holds the championship belt where it counts, linking the universe together, one photon at a time. When two black holes spiral toward catastrophe, they don't just crash, they ring the universe like a bell. In 2015, scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, caught the echoes of such a collision, a billion-year-old ripple in spacetime itself. The discovery wasn't just a triumph of engineering, it was a cosmic revelation. Those waves, born from the violent dance of black holes 30 times heavier than the Sun, raced across the cosmos at precisely the speed of light, confirming a prediction Einstein made a century earlier. Gravity, it turns out, doesn't just bend light, it moves like light, surfing the fabric of reality at the universe's ultimate speed limit. Here's how it works. Imagine spacetime as a taut trampoline. When massive objects like black holes accelerate, especially in tight orbits, they create waves that spread outward, warping the trampoline's surface as they go. These aren't just gentle undulations. The energy released by two merging black holes can briefly outshine every star in the observable universe combined. Yet unlike light, gravitational waves barely interact with matter. They pass through planets, stars, even entire galaxies as if they weren't there, stretching and squeezing everything in their path by fractions of an atom's width. LIGO genius lies in catching these infinitesimal distortions. Its twin detectors, separated by 3,000 kilometers, fire lasers down 4-kilometer-long vacuum tunnels. When a gravitational wave passes, it subtly alters the tunnel's lengths, making the lasers flicker out of sync. The signal from that first detection, WGW150914, lasted just 0.2 of a second, but it encoded a staggering story. The black hole's final orbits clocked in at half-light speed before merging into a single, more massive black hole, sending a tsunami of gravitational energy rippling outward at light speed itself. But why does gravity obey light's speed limit? The answer lies in relativity's core principle. No influence, not gravity, not information, not even space-time distortions can outpace light. If gravity acted instantly across distances, it would shatter causality, allowing effects to precede causes. Instead, just as a pebble dropped in a pond creates waves that spread at water's natural speed, mass-warping spacetime sends gravitational waves propagating at light speed. The implications are profound. When we observe light from distant events, say a supernova, we're seeing the universe's past. Now, gravitational waves add another layer, we're feeling it too. Neutron star mergers, like the one detected in 2017, emit both gravitational waves and gamma rays. Despite traveling for 130 million years, both signals arrived at Earth within 2 seconds of each other, a near-perfect tie that clinched gravity's speed once and for all. Yet mysteries remain. Some theories suggest gravitational waves might subtly slow when passing through dark matter or in the early universe's dense plasma. Others speculate that ultra-high-frequency waves beyond our current detection could reveal quantum gravity's secrets. Each new detection peels back another layer, proving that even in the darkest corners of the cosmos, the universe plays by rules written in light. Einstein's cosmic speed limit isn't just about breaking interstellar joyrides, it's the universe's ultimate referee, enforcing order in a game where cause and effect could easily spiral into chaos. Imagine if you could flick a light switch and see the bulb glow before your finger moved. Or worse, if a distant supernova's explosion reached us before the star actually died. That's the nightmare relativity prevents, weaving light's speed into the very fabric of causality like an unbreakable thread. The rule is simple. No signal, no object, no ripple in space-time can outpace light, which means no event can influence another faster than a photon could bridge the gap between them. This creates light cones' invisible boundaries separating the possible from the impossible in the cosmic arena. Picture standing at the center of two swirling hourglasses stacked tip to tip. The upward cone contains every point in space-time your actions could ever affect. The downward cone holds everything that could have ever affected you. Outside those cones, a forbidden zone where events are forever strangers, their light destined never to reach you no matter how long you wait. This elegant fencing off of causality isn't just theoretical. Particle accelerators prove it daily. When a high-energy collision creates new particles, their decay products always fly away at speeds below light's limit, never telegraphing their existence faster than nature allows. Even quantum entanglement's spooky action respects this rule. While entangled particles coordinate instantly across distance, their correlation can't be exploited to send messages faster than light without comparing notes through slower, conventional means. But here's where it gets cosmic. Black holes stretch this principle to its breaking point, cross the event horizon, and all possible light cones tilt inward toward the singularity like trees bending in a hurricane. Every future path leads downward, no escape, not even for light itself. From the outside, this looks like time freezing at the horizon as the last photons emitted by a doomed object stretch into infinite redshift. Yet from the falling observer's perspective, nothing seems amiss until spacetime's curvature becomes unbearable. Both viewpoints are correct, proving relativity's genius. Causality isn't broken, it's just wearing a disguise tailored by gravity. The real kicker, this speed limit might be why time only flows forward. Some physicists argue that if light could travel infinitely fast, the concepts of before and after would lose meaning, jumbling the universe into a soup of simultaneous events. Instead, light's finite pace gives time its arrow, ensuring heat dissipates, eggs scramble but never unscramble, and memories are records of the past rather than premonitions of the future. So the next time you grumble about light's sluggish pace across intergalactic distances, remember, it's not just a speed bump. It's the universe's masterstroke, the glue holding reality's story together, one orderly, causally coherent moment at a time. Gaze at the Hubble Space Telescope's pillar of creation, and you're staring at a cosmic magic trick, one where light's finite speed paints a portrait of stars that might already be ghosts. Those towering columns of gas and dust stretching light years tall in the Eagle Nebula aren't just a nursery for newborn stars, they're also a time machine. The light from their farthest reaches takes roughly 7,000 years to reach us, meaning some of the glittering specks embedded in those pillars could have flared out as supernova millennia ago, their death throes still racing toward Earth at light speed unseen. This illusion isn't unique to the pillar, it's a universal quirk. When we look at any distant object, we're seeing it as it was, not as it is. But the pillar's three-dimensional depth makes the effect dramatic. The nebula's base might lie slightly closer to us than its tip, so light from its top has farther to travel. A star near the base could explode today, and we'd see its violent end centuries before witnessing the same fate for a sibling star just a few light years behind it in the pillar's structure. It's like watching a fireworks show where each burst ignites at different distances. Some pops are delayed echoes of ones you've already seen. Hubble's original 1995 image only hinted at this layered history. But when the telescope revisited the pillar in 2014 with sharper optics, it revealed subtle changes. Jets of material ejected by young stars had lengthened, and pockets of gas had evaporated or collapsed further. Yet even these updates were snapshots of processes unfolding over epochs. The pillar's most famous inhabitants, the evaporating gaseous globules egg, might already have hatched their stellar embryos or been obliterated by shockwaves from supernova we haven't seen yet. The eerie beauty of this delay isn't just poetic, it's a tool. Astronomers use these light speed lags to reconstruct the pillar's true timeline. By comparing emissions from different layers, they can peel back the nebula's history like an onion skin. For example, if a star near the pillar's front emits radiation that excites gas at its back, the time lag between those two signals reveals the structure's physical depth. It's cosmic echolocation with light as the sonar ping. And here's the haunting twist. Some theories suggest one or more of the pillar's massive stars have already died, their explosions sending destructive shockwaves rippling through the gas. If so, the next generation of telescopes might capture the pillar's disintegration in real time, watching as a shockwave, traveling at a fraction of light speed, tears through those delicate tendrils of dust. The irony, by the time we see it happen, the event will be ancient history, the nebulous fate sealed long before human civilization began. This is the universe's ultimate sleight of hand, a celestial tableau where the present is always just out of reach, and every observation is a window into a past we can never touch. The pillar of creation isn't just a photograph, it's a palimpsest of cosmic time, written in light and shadow, where the stars' stories unfold at the speed of patience itself. The sun isn't just a glowing ball of light. It's a cosmic particle accelerator capable of flinging chunks of itself across the solar system at nearly the speed of light. During a coronal mass ejection, or CME, the sun's magnetic fields snap like overstretched rubber bands, launching billions of tons of superheated plasma into space. But hidden in that chaos are individual protons, whipped to velocities so extreme they could lap Earth 7 times in a single second. These aren't just fast, they're interplanetary bullets, packing enough energy to pierce through spacecraft hulls and astronaut flesh like tissue paper. What makes this acceleration possible? It's a combination of brute force and precision. As the sun's tangled magnetic fields reconnect, they release staggering amounts of energy, equivalent to millions of hydrogen bombs detonating at once. Protons caught in this maelstrom get catapulted outward, riding shock waves that act like natural particle accelerators. Some of these protons reach 90% of light speed in mere minutes, a feat that would require a machine like CERN Large Hadron Collider to replicate on Earth. And unlike lab experiments, the sun does this casually, repeatedly, as part of its everyday weather. For astronauts, these solar storms are more than just a spectacle, they're a silent crisis. Imagine being on the moon during a major CME. With no atmosphere to scatter the protons, your body would absorb their full fury. Within hours, you'd suffer radiation sickness, with DNA damage mounting like a time lapse of decay. Even aboard the International Space Station, shielded by Earth's magnetic field, astronauts report seeing flashes of light behind closed eyelids during solar storms, their retinas getting bombarded by high-energy protons punching through the station's walls. The real danger lies in the unpredictability. Unlike gamma-ray bursts or supernova, which are rare and distant, CMEs can strike with little warning. In 2012, a storm of this magnitude missed Earth by just 9 days, a near miss that, had it hit, could have knocked out satellites, power grids, and left astronauts on Mars missions facing lethal doses. Future lunar or Martian colonists won't have Earth's magnetic umbrella. Their survival might depend on storm shelters lined with water or polyethylene, materials dense enough to slow these light-speed projectiles. Yet there's an eerie beauty to this violence. When these protons collide with Earth's atmosphere, they spark auroras so vivid they've been mistaken for dawn. The so-called Great Aurora of 1859 turned night into day as far south as Cuba. Today, we understand these events as cosmic reminders. Light speed isn't just a theoretical limit. It's a force that shapes and sometimes threatens our fragile place in the cosmos. Neutron stars are nature's funhouse mirrors, warping light so severely that if you stood on one surface, assuming you could survive the trillion-G gravity, you'd see the back of your own head staring at you. These cosmic remnants, packing more mass than the sun into a sphere the size of Manhattan, don't just bend light, they tie it into knots. Photons whipping around their surfaces must contend with gravity so intense that even light's straight-line path gets twisted into a pretzel, creating optical illusions that defy common sense. Take the phenomenon of multiple images. A neutron star's gravitational field can act like a lens, splitting light from a distant star or galaxy into duplicate copies. Imagine looking up and seeing not one but two, three, or even a full ring of suns circling the sky, each a ghostly echo of the same celestial object. This isn't science fiction, it's gravitational lensing cranked up to 11. The star's crushing density means photons skimming close enough get bent into multiple paths, like beams of light ricocheting through a hall of mirrors. Some trajectories loop so tightly they circle the star multiple times before escaping, delivering snapshots of the same object from slightly different angles. The real kicker, time warps along with the light. A photon grazing the surface experiences such extreme time dilation that while it might take years to complete a loop from our perspective, from the photon's view, it's a blink. This means some of those duplicate images could show the same star at different points in its history, like catching a single actor playing multiple roles in a cosmic movie, except the roles are separated by decades. And then there's the color shift. Light struggling to climb out of a neutron star's gravity loses energy, reddening dramatically. What started as blue starlight might reach us as faint infrared, drained by the effort. This redshift isn't just a curiosity, it's a lifeline for astronomers. By measuring how much a neutron star's gravity alters the light passing near it, scientists can weigh these ultra-dense objects with precision, confirming they really are as monstrously compact as theory predicts. But the wildest twist might be what this means for any potential neutron star auroras. Unlike Earth's northern lights powered by solar particles, a neutron star's light show could literally wrap around itself. Charged particles spiraling along magnetic field lines might emit light that loops the star multiple times before escaping, creating glowing coronas that appear to hover impossibly above the surface. From certain angles, you might even see a single particle's afterimage trailing behind it like a comet's tail, an echo of where it was moments earlier thanks to light's delayed escape. This extreme lensing isn't just a cosmic oddity, it's a stress test for relativity. Every photon's twisted path confirms Einstein's equations under conditions no lab could ever replicate. And somewhere in that tangle of light and gravity lies a clue to how spacetime behaves when pushed to the breaking point, a preview of physics we're only beginning to dream of. So while we'll never stand on a neutron star's surface, their warped light offers the next best thing, a front-row seat to the universe's most extreme magic show. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt in the 1970s, they carried humanity's first messages to the star's gold plaques etched with drawings of a man and woman. But these trailblazing probes left behind another, far more perplexing legacy, an unsolved motion anomaly that haunted physicists for decades. As the twins drifted toward interstellar space, tracking data revealed they were slowing down slightly more than gravity alone could explain a discrepancy no bigger than a snowfall's effect on a moving car, yet utterly inexplicable under known physics. This Pioneer anomaly became one of space exploration's most stubborn mysteries, with some even speculating it hinted at flaws in Einstein's relativity. The numbers were maddeningly precise. Both Pioneers experienced a constant deceleration of about 8.74 times 10 to the negative 10th meters per second squared, roughly 10 billion times weaker than Earth's gravity, but persistent across billions of kilometers. At first, scientists suspected mundane causes, leaking fuel, outgassing from insulation, even the minuscule pressure of sunlight, but calculations ruled these out. The anomaly held firm through multiple independent analyses, sparking wilder theories perhaps dark matter was dragging on the probes, or unknown modifications to gravity were at play. Some papers even suggested light itself might behave differently over vast interstellar distances, subtly altering how spacecraft moved. The breakthrough came not from rewriting physics textbooks, but from kitchen-grade thermodynamics. Engineers realized the pioneers' radioactive power sources, plutonium-filled spheres called RTGs, were emitting heat asymmetrically. As these warm modules radiated infrared photons in random directions, they created a tiny recoil force. Think of it like sitting in a swivel chair and shining a flashlight. Each photon you emit gives you an imperceptible nudge in the opposite direction. Over decades, in the frictionless vacuum of space, these infinitesimal kicks added up to the exact observed deceleration. The clincher, when scientists reconstructed the pioneers' thermal profiles using archival data, accounting for every watt of heat radiating from their lopsided designs, the anomaly vanished. What once seemed like a crack in fundamental physics was just the universe's quietest propulsion system, photons nudging spacecraft at the speed of light, one infrared whisper at a time. This cosmic detective story holds a profound lesson. Sometimes the most exotic explanations hide in the most ordinary phenomena. The pioneers' gentle slowdown wasn't a rebellion against relativity. It was a masterclass in how light's momentum shapes reality, even when we forget to account for its push. And somewhere in that realization lies the true heart of exploration, not just racing toward the unknown, but learning to notice the subtle forces guiding us along the way. Driving a car on Earth is easy. You turn the wheel and instantly the car responds. But try steering a rover on Mars, and suddenly you're playing the universe's most frustrating video game, where every command has a built-in lag of anywhere between 5 and 20 minutes, depending on where Earth and Mars are in their orbits. That's the reality of light-speed communication. Delays a hurdle that turns even simple tasks into high-stakes puzzles. Take NASA's Perseverance rover. When it landed in Jezero crater in 2021, Mission Control didn't watch events unfold in real time. They watched history. The rover's signals, traveling at light speed, took over 11 minutes to cross the gulf between Mars and Earth. By the time engineers received confirmation the rover had entered Mars' atmosphere, Perseverance had already been safely on the surface or smashed to pieces for nearly a quarter of an hour. This delay isn't just inconvenient, it rewrites the entire playbook for space exploration. Here's where it gets fascinating. Rovers aren't remotely controlled like drones. They're more like pre-programmed mail carriers, executing batches of commands uploaded at the start of each Martian day. Engineers spend hours meticulously planning every movement, where to drive, which rocks to zap with lasers, where to drill for samples, then beam those instructions across space and wait. A drive that might take 10 minutes on Earth unfolds over days on Mars, with each maneuver requiring careful verification before the next step is sent. One wrong move and the rover could tumble into a sand trap or scrape its belly on jagged terrain with no hope of rescue. The delays create surreal challenges. When Perseverance's helicopter companion, Ingenuity, took its first flight, Mission Control celebrated 90 seconds after the helicopter had already landed. And if something goes wrong, engineers can't just hit pause. In 2012, during the Curiosity rover's mission, a software glitch forced the team to wait 36 agonizing hours, a full Martian day, before they could diagnose and fix the issue. All the while, the rover sat idle under an alien sky, its human handlers helpless until light could ferry their solutions across the void. These delays expose a fundamental truth about our place in the cosmos. Even at light speed, the fastest possible communication in the universe, the vastness of space imposes a patience we're unaccustomed to on Earth. Future crewed missions to Mars will face the same hurdle, forcing astronauts to operate with unprecedented autonomy. Imagine performing surgery with a 20-minute lag between your scalpel's motion and the patient's response, or building a habitat where every instruction to robots arrives too late to correct mistakes. It's a paradigm shift humanity must master if we're to become an interplanetary species. Yet within this constraint lies ingenuity. rovers like Perseverance are packed with AI to make split-second decisions, avoiding obstacles, selecting science targets without waiting for Earth's input. Future missions might deploy networks of relay satellites to streamline communication, or use predictive algorithms to anticipate problems before they arise. But no matter how advanced our tech becomes, one law remains unbreakable. In space, every conversation is a message in a bottle, tossed into the cosmic ocean at the speed of light, leaving us to wait and wonder until the reply washes ashore. One of the universe's cruelest illusions plays out at the edge of a black hole, where time itself becomes a hall of mirrors. To a distant observer watching an object fall toward the event horizon, something bizarre happens. The closer it gets, the slower it appears to move, until it seems to freeze in place like a bug trapped in amber. This isn't just a trick of perspective, it's the universe enforcing one of relativity's strangest predictions: infinite time dilation. Picture an astronaut plunging toward a black hole, their ship transmitting a farewell signal back to Earth. As they approach the event horizon, their clock, from our viewpoint, ticks ever slower. At first, the delay is subtle, but with every meter closer, the gravitational time stretch grows more extreme. By the time they're a hair's breadth from the horizon, seconds for them could equal centuries for us. Their final approach stretches into eternity, their image redshifted into invisibility as the light struggles to escape the black hole's grip. From our vantage point, they never actually cross the threshold. They just fade into a dim, motionless smear on the cosmic background. But here's the twist: the astronaut experiences none of this drama. For them, time flows normally. They cross the horizon in finite time, unaware of the frozen tableau they've left behind in the universe's memory. This paradox reveals the dual nature of space-time. What's infinite for one observer is routine for another. It's like watching a movie where the protagonist steps through a door, but the audience sees them pause mid-stride, forever suspended in the frame. The physics behind this illusion hinges on light's desperate escape attempt. Photons emitted near the event horizon must climb out of an impossibly steep gravitational well, sacrificing nearly all their energy in the process. Their wavelengths stretch to radio frequencies, then beyond, until they're effectively erased from the visible universe. Meanwhile, the interval between arriving photons grows longer and longer, creating the illusion of a slowdown. The signal doesn't just dim, it thins, like a recording played at an ever-slowing speed until the final note never comes. This eerie effect isn't just theoretical. When astronomers study matter spiraling into supermassive black holes like Sagittarius, a star at our galaxy's center, they catch glimpses of this relativistic freeze frame. Hot gas clouds don't vanish abruptly. They smear across telescopes' readings, their light stretched and diluted by the black hole's spacetime warping. It's as if the universe itself hits pause on the brink of oblivion. Yet buried in this illusion is a profound truth about black holes and reality itself. The frozen star effect isn't proof that nothing ever crosses the horizon. It's evidence that the horizon is a one-way curtain, a point where the universe's causal threads are snipped. What happens beyond it isn't just hidden, it's severed from our timeline entirely, existing in a realm where our laws of physics lose all meaning. The astronaut's fate isn't unknown, it's unknowable, sealed away by the speed of light's ultimate surrender to gravity's might. So when you see those artists' renderings of black holes with stars frozen at their edges, remember, you're not looking at a scientific inaccuracy. You're witnessing the universe's last stand against the abyss, a cosmic sleight of hand where light's finite speed paints a masterpiece of deception. And somewhere in that illusion lies the boundary between what we can see and what we're forever barred from knowing. Hubble's deep field images reveal galaxies fleeing from us so fast that they seem to break the universe's ultimate speed limit. But this isn't a cosmic crime scene, it's a masterpiece of relativity's sleight of hand. When astronomers say certain galaxies recede faster than light, they're not claiming these objects are zooming through space like rogue rockets. Instead, it's the expansion of space itself that stretches the distances between us and these galaxies so rapidly that their light struggles to keep up, creating an illusion of superluminal motion. Here's how this cosmic magic trick works. Imagine two ants on an inflating balloon crawling away from each other at a steady pace. Even if their tiny legs move slowly, the balloon's expansion can make the distance between them grow faster than either ant could crawl on its own. Now replace the ants with galaxies and the balloon with the fabric of space-time. The galaxies aren't speeding through space. Space is stretching between them, carrying them apart like raisins in rising bread dough. When this expansion outpaces light's ability to bridge the gap, we perceive them as moving faster than light, even though no local physics is being violated. The key lies in redshift, the stretching of light's wavelength as space expands during its journey. A galaxy racing away at near light speeds emits light that arrives dramatically reddened, like a siren dropping in pitch as an ambulance speeds away. But for the most distant galaxies, this redshift becomes so extreme that their light stretches into radio waves or beyond, their visible light dimmed to nothingness by the relentless expansion. Some galaxies observed by Hubble are so far that their light has taken over 13 billion years to reach us, and during that time, the space between us has stretched so much that they now appear to recede at over 3 times light speed. This doesn't mean we're watching them live in some forbidden FTL state. We're seeing their ancient light emitted when the universe was young and space was far more compact. By the time that light arrives, the galaxy's true position has been carried away by expansion to a distance so vast that its current recession velocity exceeds light speed. It's like receiving a letter from a friend who's since moved to a distant country. The message is old, and the sender's present location is far beyond where the letter originated. The real twist: these galaxies aren't special. From their perspective, we're the ones appearing to flee faster than light. The universe has no center, just an ever-stretching canvas where every observer sees the same illusion of being at rest while the cosmos races away. And as expansion accelerates due to dark energy, more and more galaxies will cross this phantom threshold, their light frozen in transit, their stories forever severed from our future. But here's the beautiful paradox: even as these galaxies vanish from our causal horizon, their ancient photons still reach us, carrying snapshots of the universe's youth. Each redshifted galaxy in Hubble's deep fields is a message in a bottle, cast across an ocean of expanding spacetime, a reminder that light's speed isn't just a limit, but a bridge between the past's fiery dawn and our present glimpse into the abyss. In the vast expanse of the cosmos, light is known as the ultimate speedster, but in a Harvard lab in 1999, scientists performed a feat that would make even photons seem sluggish. They hit the brakes on light itself, slowing it down from its blistering 299 million meters per second to a leisurely 17 meters per second, about the speed of a bicycle coasting down a quiet street. The key to this cosmic traffic jam: a bizarre state of matter so cold and strange it defies everyday logic, the bose-Einstein condensate. To understand this achievement, picture matter in its most subdued form. When cooled to temperatures just a whisper above absolute zero, around 459.67 degrees below 0 Fahrenheit, certain gases like rubidium or sodium atoms stop behaving like individual particles and merge into a single quantum wave. This surreal substance, predicted by Einstein and Satyendra Nath Bose in the 1920s, is so fragile that even a stray photon can shatter it. But it's also the perfect medium for tampering with light's velocity. Here's the trick: when laser light enters this ultra-cold cloud, its photons interact with the condensate's atoms in a delicate quantum tango. The light's energy gets temporarily absorbed, turning the atoms into a kind of memory of the photon's properties. These excited atoms then re-emit the photons on the other side, but with a crucial delay. It's as if light is passing through a hallway lined with doors. Each door briefly swallows the light before spitting it out again, creating a staggered, slowed-down procession. The result, light that creeps along at paces you could outrun on a skateboard. The implications are as profound as they are strange. By tuning the condensate's density and temperature, researchers can essentially dial light's speed up or down like a volume knob. In some experiments, they've even brought light to a complete standstill, storing its information in the atomic cloud before releasing it intact moments later. A quantum pause button that could revolutionize secure communication. Imagine sending a message encoded in light, halting it mid-journey inside a condensate, then resuming its path only when safe from eavesdroppers. But the real magic lies in what this reveals about light's true nature. Despite moving at a crawl, the photons in these experiments never violate relativity's speed limit. Their group velocity, the speed at which their wave peaks travel, slows dramatically, but the underlying phase velocity of their quantum oscillations still clocks in at light speed. It's a reminder that light's behavior is as much about its environment as its inherent properties. This duality opens doors to technologies once confined to sci-fi. Quantum computers could use slowed light to mediate interactions between qubits, while ultra-precise sensors might detect gravitational waves by measuring subtle changes in light's speed through controlled atomic clouds. Even astronomy could benefit. Simulated bose-einstein conditions might help us understand how light behaves in extreme cosmic environments, like neutron star atmospheres or the early universe's primordial soup. Yet beyond the applications, this research humbles us. The same light that crosses galactic voids in eons can also be coaxed into a leisurely stroll, proof that the universe's rules are flexible enough to accommodate both the unimaginably fast and the painstakingly slow. And somewhere in that dichotomy lies a deeper truth. Speed, much like time, is never absolute. It's simply a conversation between light and the strange quantum stage it walks upon. Black holes devour everything that crosses their event horizon. But what if the universe has cosmic fountains to match those cosmic drains? Enter the mysterious white hole, a hypothetical twin to the black hole that flips the script entirely. While black holes greedily suck in matter and light, their theoretical counterparts would violently expel everything outward, spitting energy and particles into space at, or even beyond, light speed. Imagine a black hole's time-reversed twin, an object where nothing can enter, only escape, as if the universe itself pressed rewind on gravitational collapse. The math behind white holes isn't science fiction, it's buried in the same equations Einstein crafted for black holes. General relativity treats spacetime as a flexible fabric, and its solutions are symmetric. If a black hole is a one-way tunnel where matter vanishes, a white hole would be its exit ramp, an origin point where that same matter bursts back into existence. Some physicists even speculate that black holes and white holes could be connected via wormholes, forming bridges between distant regions of spacetime. The catch: any matter ejected from a white hole would be shredded into its most fundamental particles, a cosmic smoothie of energy and radiation. But if white holes exist, where are they? The challenge is that, unlike black holes which form naturally from collapsing stars, white holes would require exotic conditions to arise. One leading theory suggests they might be remnants of black holes that somehow bounced back after evaporating via Hawking radiation, though this remains speculative. Others propose that white holes could be the birth cries of new universes, with the Big Bang itself acting as the ultimate white hole event. After all, our own universe erupted from an incomprehensibly dense state, spewing matter outward at unimaginable speeds, a description eerily similar to what a white hole might look like from the inside. Observational clues are scarce but tantalizing. In 2006, astronomers detected a bizarre gamma-ray burst, GRB 060614, that defied explanation. Unlike typical bursts tied to supernova or neutron star collisions, This event lasted just 102 seconds and left no visible aftermath, no fading glow, no stellar corpse. Some researchers floated the idea that it might have been a white hole's brief, violent eruption, a singularity coughing up energy before snapping shut. Another candidate, the so-called dark explosions observed in distant galaxies, could theoretically be white holes ejecting matter too fast for conventional telescopes to track. The wildest implication, white holes might solve one of physics' biggest paradoxes, the black hole information problem. If black holes swallow information forever, it violates quantum mechanics' rule that information can't be destroyed. But if every black hole births a white hole elsewhere, perhaps in another universe, that information could be preserved, just hopelessly scattered. It's a cosmic game of hide and seek where the universe itself holds the final clue. For now, white holes remain a breathtaking what if a reminder that even gravity's darkest secrets might have luminous counterparts. Whether they're lurking in distant galaxies or woven into the Big Bang's echo, one thing's certain. If they're real, they'd rewrite the cosmic rulebook, proving that even light speed isn't the end of the story. It's just the beginning of something far stranger. Quantum entanglement might seem like the universe's ultimate cheat code, a way for particles to coordinate instantly across cosmic distances, as if thumbing their noses at Einstein's speed limit. But here's the catch that keeps physicists up at night. This spooky connection, while instantaneous, can't actually send information faster than light. It's like having a pair of magical dice that always land on matching numbers, no matter how far apart they're rolled, except you can't control which number appears. Take quantum computing, where qubits, the quantum version of bits, leverage entanglement to perform mind-bending calculations. When two qubits are entangled, measuring one immediately determines the state of the other, even if they're light years apart. This phenomenon powers quantum algorithms that could someday crack encryption or simulate complex molecules, but try to use that link to send a message and the universe slams the brakes. The problem, entanglement's coordination is random. You can't force a qubit to flip to a specific state to encode a 1 or 0. The outcome is always probabilistic. It's like trying to communicate by telepathically guessing card draws with a partner. You'll always have matching cards, but neither of you chose them. This limitation isn't just a technical hiccup, it's woven into quantum mechanics' core. Imagine Alice and Bob, the classic duo in physics thought experiments, each holding one half of an entangled qubit pair. If Alice measures her qubit and gets a 1, Bob's instantly becomes 1, 2, but Bob has no way of knowing whether his qubit state came from Alice's measurement or pure chance. To confirm the correlation, Alice must send him a classical message by email, radio, or carrier pigeon, and that message crawls along at light speed or slower. Entanglement's instant link is useless without this slower backup, making faster-than-light communication impossible. The universe enforces this rule with quantum no-cloning theorem, which forbids copying an unknown quantum state, and the no-communication theorem, which mathematically guarantees entanglement can't transmit data. These aren't just abstract hurdles, they're cosmic traffic cops, ensuring causality isn't upended by quantum weirdness. Break them, and you could send signals backward in time, creating paradoxes where effects precede causes. Yet here's the tantalizing loophole. While entanglement can't directly send messages, it enables something almost as powerful: quantum teleportation. By combining entangled qubits with classical communication, scientists can teleport a quantum state from one location to another. It's not Star Trek-style matter transport. It's more like faxing a fragile original by first shredding it, then using entangled particles as a guide to perfectly reconstruct the copy elsewhere. The process still respects light speed, since the classical instructions lag behind, but it hints at a future where quantum networks might shuttle unhackable encryption keys or link quantum computers across continents, all while keeping relativity's speed limit firmly intact. So while entanglement defies intuition, it's no rebel. It plays by the universe's deepest rules, offering a glimpse of reality's quantum scaffolding without ever letting us hijack it for superluminal gossip. And that's the real magic, not breaking light speed, but discovering how the cosmos keeps everything in balance, even when it seems to bend its own laws. On August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a signal so powerful and peculiar that the astronomer who discovered it scribbled, "Wow," in the margin of the printout, giving the phenomenon its now iconic name. For 72 seconds, the Big Ear radio telescope locked onto a narrowband radio burst blazing at 40 times the noise level of deep space, transmitting at precisely the frequency hydrogen resonates across the cosmos. Then, just as abruptly as it began, the signal vanished, leaving behind one of astronomy's greatest unsolved mysteries, and a pulse of electromagnetic waves that, if it came from a distant civilization, has been racing through the void at light speed for nearly half a century. The WOW signal wasn't just strong, it was textbook perfect for an artificial transmission. Tuned to 1420 MHz, the watering hole frequency where hydrogen, the universe's most abundant element, naturally emits, it matched predictions for how an advanced civilization might broadcast its presence. Unlike cosmic static or pulsar bursts, the signal was narrowly focused, undrifting, and silent except for that singular, screaming spike, even more intriguing. It originated from the direction of the Sagittarius constellation, a star-rich region near our galaxy's core where millions of potential habitable worlds could exist. But here's the cosmic twist. By the time we heard it, whatever produced the WOW signal might have already gone dark. If it came from a star system 100 light-years away, those radio waves left their source when humans were just inventing radio itself, meaning any civilization behind it wouldn't know we were here to listen. And if it traveled farther, the light-speed delay becomes even more haunting. A signal from 1,000 light-years away would have begun its journey when Earth's brightest minds were debating whether the stars were holes in a celestial dome. The sheer scale of time and distance turns every hypothesis into a Rorschach test. Are we chasing aliens, a bizarre astrophysical anomaly, or an echo of something else entirely? Astronomers have scoured the same patch of sky for repeats, deploying modern arrays like the Very Large Array and Breakthrough Listen, yet silence reigns. Some argue it could have been a comet's hydrogen cloud reflecting sunlight, except comets weren't in the area that night. Others suggest a military satellite or secret experiment, though no records match. The most chilling possibility, it was intentional, a cosmic hello aimed our way but sent on a schedule we weren't meant to miss, a 72-second window inviting a reply we didn't know how to send in time. Now, nearly 50 years later, that pulse of energy, if artificial, is still out there, expanding into the galaxy at light speed, carrying its message towards stars we've yet to name. And somewhere in the vastness, another civilization might be tuning their own telescopes, waiting for a signal we haven't even thought to send, the WOW signal isn't just a mystery, it's a ticking clock counting down the moments until the universe decides if we're ready to join the conversation. For centuries, the meter was a human-sized concept, originally defined as 1/10,000,000th of the distance from the North Pole to the equator, then later by a carefully crafted platinum iridium bar locked in a vault near Paris. But in 1983, humanity traded tangible rulers for the unwavering constancy of light itself. Today, the meter isn't measured by scratches on metal or marks on a stick. It's defined by how far light travels in a vacuum in 1/299,792,458th of a second. This shift from physical artifact to cosmic constant didn't just change how we measure, it revealed light as the universe's ultimate ruler. The journey to this definition was born from frustration. For decades, scientists relied on the International Prototype Meter, a gleaming X-shaped bar stored under glass at the International Bureau of Weights and Measures. But physical objects warp, scratch, and degrade even under ideal conditions. By the mid-20th century, measurements precise enough to detect atomic-scale imperfections exposed the bar's limitations. The quest for a universal standard led to light, whose speed Einstein had enshrined as nature's most reliable yardstick. After centuries of Earth-bound definitions, humanity finally anchored its units to the fabric of spacetime itself. Here's how it works. Light speed in a vacuum, 299,792,458 meters per second, is now a fixed value with zero uncertainty. This means the meter is no longer an arbitrary length. It's a fraction of light's unwavering journey through emptiness. Practical applications are everywhere. Laser interferometers, which bounce light off mirrors to measure infinitesimal distances, rely on this definition to calibrate everything from silicon chip manufacturing to gravitational wave detectors like LIGO. When scientists confirmed the first ripples in spacetime in 2015, they were effectively measuring distortions smaller than 1,000th the width of a proton using light speed as their guide. The irony, this precision traces back to a cosmic contradiction. Light speed is both immeasurably fast and agonizingly slow, a snail's pace for interstellar travel, yet instantaneous for human-scale tasks. By tethering our units to it, we've embraced relativity's central truth. The universe doesn't care about our convenient divisions of space and time. It operates on a scale where light speed isn't just a number, it's the exchange rate between dimensions, the invisible thread stitching reality together. And somewhere in that realization lies the meter's true brilliance. It's no longer a human invention, but a cosmic revelation, a reminder that even our most mundane tools are whispers of the universe's deepest laws. The universe has a ghostly echo, a faint glow that fills every cubic centimeter of space, saturating the cosmos with whispers from its fiery birth. This is the cosmic microwave background, the oldest light in existence, racing toward us at light speed for 13.8 billion years from the edge of time itself. It's not just radiation, it's the universe's baby picture, a snapshot of reality when it was a mere 380,000 years old, transformed from a seething plasma into a transparent sea of atoms. Picture the early universe as a scorching fog so dense that light couldn't travel more than a fraction of an inch before crashing into another particle. But as expansion cooled the cosmos, protons and electrons finally combined into neutral hydrogen, unleashing photons in a sudden flash, the moment light broke free. Those primordial photons, once blazing with the heat of a newborn universe, have stretched with the expanding fabric of space, their wavelengths lengthening from visible light into microwaves, their energy diluted to a mere 2.7 degrees above absolute zero. Yet they're everywhere. Even the empty space between galaxies hums with this ancient afterglow. Hold up an old-fashioned TV between channels, and about 1% of that static comes from this relic radiation, a broadcast from the dawn of time. What's astonishing isn't just its omnipresence, but its perfection. The CMB is a near-uniform sea of microwaves, varying by less than 1 part in 100,000 across the sky, evidence of the universe's startling smoothness in infancy. Yet buried in those tiny fluctuations are the seeds of everything we know. Slightly denser regions, imprinted as warmer spots in the CMB, became the gravitational wells where galaxies would later form. It's as if the universe left behind a coded blueprint, and we're only now learning to read it. Modern telescopes like Planck and WMAP have mapped these variations with exquisite precision, revealing patterns that confirm dark matter's grip and dark energy's push. But the CMB holds deeper mysteries. Some theories suggest its large-scale anomalies like the Erie cold spot, a vast region cooler than expected, could hint at collisions with other universes in a multiverse. Others propose that subtle twists in the light's polarization might carry echoes of gravitational waves from the universe's first trillionth of a second, a window into inflation's violent dawn. And here's the humbling truth: every second, trillions of these primordial photons pass harmlessly through your body, unnoticed relics of a time before stars, before planets, before atoms could even bond into molecules. They've outlasted quasars, witnessed the birth and death of galaxies, and traveled farther than anything else ever could, only to end their journey as whispers in our radio telescopes. The cosmic microwave background isn't just light, it's the universe's first breath, fossilized in photons, still carrying the heat of creation across the aeons. The Milky Way alone contains hundreds of billions of stars, with planets outnumbering grains of sand on Earth. So where is everybody? This is the heart of the Fermi paradox, the glaring contradiction between the high probability of alien civilizations and the utter silence we hear from the cosmos. One answer might lie in the universe's strict speed limit. Light itself could be the ultimate barrier, trapping civilizations in bubbles of isolation across the galaxy's vast reaches. Consider the math. Even if life were common, the distances between stars create communication delays measured in decades or centuries. A signal sent from a planet orbiting Proxima Centauri, our nearest stellar neighbor, would take over 4 years just to reach Earth, and that's assuming they're aiming directly at us. For civilizations scattered across the galaxy, two-way conversations become impossible. By the time a question is answered, millennia could pass, cultures could rise and fall, and the original senders might not even exist anymore. It's like trying to have a phone call where each reply takes generations. The conversation collapses under the weight of time. This isn't just about patience, it's about practicality. Imagine a civilization broadcasting signals in all directions, hoping someone will listen. For their messages to reach even a fraction of the Milky Way stars, they'd need to sustain their efforts for millions of years, far longer than any human society has existed. And if they're targeting specific planets, the odds grow even slimmer. Earth, for instance, has only been detectable through radio waves for about a century, a blink in cosmic terms. Any civilization more than 100 light-years away wouldn't even know we're here yet the silence might run deeper. Some theories suggest advanced societies could abandon radio communication entirely, switching to neutrino beams or quantum entanglement, technologies we can't yet detect. Others argue that civilizations inevitably hit a great filter, a catastrophic event like climate collapse or AI rebellion, that prevents them from reaching the stars. But the simplest explanation might be the most humbling. Space is just too big and light too slow for anyone to find each other before time or distance swallows the opportunity. Even our own attempts to connect highlight the problem. The Arecibo message beamed toward a star cluster in 1974 won't arrive for 25,000 years, and any reply would take just as long to return. By then, humanity could be extinct, evolved beyond recognition, or spread across the galaxy. The very act of reaching out becomes a message in a bottle, tossed into an ocean where the currents move at light speed far too slow to ever expect a reply. So the Fermi paradox might not be a paradox at all. The universe could be teeming with life, all shouting into the void, their signals spreading at the speed of light but still too sluggish to bridge the gaps between stars. We're not alone, we're just early or far apart, or worse, perpetually out of sync with civilizations whose calls we'll never hear in time. Breaking the cosmic speed limit isn't just an engineering challenge, it's a rebellion against the universe's deepest laws. For over a century, Einstein's relativity has stood as an unshakable truth. Nothing with mass can reach, let alone surpass, the speed of light. The energy required grows exponentially as you approach that limit, becoming infinite at the threshold. Yet in laboratories and theoretical papers, scientists keep probing for loopholes in this universal law, dreaming of shortcuts that might let us leapfrog across the galaxy without technically breaking the rules. One tantalizing possibility: wormholes, hypothetical tunnels through space-time that could connect distant points like cosmic subway lines. The math allows for these Einstein-Rosen bridges, but there's a catch. They'd require exotic matter with negative energy to stay open, a substance we've never observed. Imagine trying to prop open a black hole's throat with anti-gravity glue while avoiding instant collapse into a singularity. Even if we could stabilize one, passing through might trigger catastrophic feedback loops or expose travelers to lethal tidal forces. The late physicist Stephen Hawking speculated that wormholes would likely self-destruct the moment anything tried traversing them, a cosmic booby trap preserving causality at all costs. Then there's the Alcubierre warp drive, which cheats by moving space itself rather than traveling through it. By compressing space-time ahead of a ship and expanding it behind, the vessel could effectively ride a wave of distorted reality while never locally exceeding light speed. Early calculations suggested this would demand more energy than exists in the observable universe, but recent refinements propose harnessing dark energy or hypothetical quantum fields to reduce the requirement. The showstopper, creating the warp bubble, might unleash deadly particle bursts at the destination. Imagine arriving at Alpha Centauri, only to vaporize it with an unintended gamma-ray tsunami. These dilemmas reveal a deeper truth. Faster-than-light travel isn't just about propulsion. It's about navigating a minefield of paradoxes. Special relativity insists that exceeding light speed in any frame of reference would reverse cause and effect, opening doors to time travel. Would a message sent faster than light arrive before it was transmitted? Could a warship erase its own ancestors from history? The universe seems hardwired to prevent such violations, whether through quantum noise destroying wormholes or Hawking radiation frying time machines. Yet perhaps the greatest barrier isn't physics, it's ethics. If humanity somehow cracked FTL technology, who would control it? The weaponization potential is staggering. A pebble accelerated to relativistic speeds could impact with the force of a nuclear bomb. And cultural contamination might prove equally destructive. Imagine colonists arriving at an exoplanet only to introduce microbes that decimate native ecosystems. The prime directive from Star Trek wasn't just sci-fi speculation. It reflects genuine concerns about our responsibility as a potentially galaxy-altering species. So will we ever dance among the stars at warp speed? The answer may lie not in overcoming light's barrier, but in redefining the question. Quantum entanglement proves the universe has non-local connections we barely understand. Dark energy's accelerating expansion hints at hidden forces bending spacetime in ways we can't yet harness. Maybe the key isn't breaking light's speed limit, but learning to read the cosmic fine print that governs when and how it can be bent. After all, the universe didn't give us curiosity and ingenuity to surrender to impossibility. It gave them to us to discover which rules are written in stone and which are merely waiting to be rewritten. From frozen light in ultra-cold quantum labs to galaxies fleeing faster than light itself, these 30 mind-bending facts reveal one undeniable truth: the speed of light isn't just a number on a page. It's the universe's ultimate storyteller, shaping everything from the birth of stars to the fate of civilizations. We've seen how light bends under black holes' grip, races through fiber optic cables at a crawl, and even gets outrun by cosmic shadows in a game of celestial sleight of hand. We've watched entangled particles defy distance without breaking light's rules, and glimpsed warp drives that twist space-time itself to skirt the speed limit. Each discovery peels back another layer of reality, proving that light's extremes aren't anomalies, they're the universe's way of whispering its deepest secrets. Think about this. Every photon from the cosmic microwave background has been traveling for over 13 billion years just to reach your eyes, carrying echoes of the Big Bang itself. Neutrinos slice through planets like ghosts, while gamma-ray bursts pack a star's lifetime of energy into seconds. And somewhere out there, the wow signal might still be racing through the void, waiting for someone or something to finally reply. The more we learn, the clearer it becomes. Light's speed isn't a barrier. It's a key, one that unlocks black holes, stitches together quantum realms, and bridges the past with the present. So here's the real question. What's left to discover? Could white holes be lurking in forgotten corners of space-time? Will we ever decode quantum entanglement's hidden language? Or will dark energies accelerating expansion rewrite the rules entirely? The universe is far stranger than we've dared to imagine, and every answer only leads to wilder questions. If you've made it this far, you're not just watching a video, you're joining a cosmic detective story that's still unfolding. Help us keep exploring the impossible. Smash that like button if your mind's been blown. Subscribe to stay on the light speed frontier, and let us know in the comments which fact left you staring at the sky, questioning everything. The universe isn't done surprising us yet, and neither are we. End screen with suggested videos. Subscribe and